Hello students, it's Dr. Sansom, and I want to talk to you for a minute about resonance. Resonance is a concept that we talk about when we're dealing with Lewis structures. And resonance happens when there are multiple equivalent ways to arrange the electrons in a molecule or ion. And I want to point out that we are using resonance because Lewis structures as a whole are just models of molecules. They're not real. So when we talk about resonance structures, they're also not real, but they help us understand the structure of the molecule better. So I'm going to do a couple of examples here. The first one that I want to do is carbonate ion. So I'm going to follow my rules for drawing Lewis structures. I'll have my carbon in the middle, and I'll have my oxygens around the outside. I get 4 electrons from carbon, 18 electrons from oxygen, and 2 extra because it's a negative ion, so that gives me 24 total electrons to work with. I'm going to fill in my single bonds. That's 6 electrons. I'll have 8, 10, 12, 14, 16, 18, 20, 22, 24. So I will use up all my electrons, but my carbon in the middle here doesn't have an octet yet. So I'm going to have to make a double bond. Now this is the key point in this process that I want you to notice. Could I make my double bond on the left, on the top, on the right? I could choose any of those and it would be totally equivalent. They're all oxygen atoms that are currently making a single bond to my carbon. I'm going to start by making a double bond on the right, just for fun because I feel like it. I could have chosen any one of them, but that's where I chose to make my double bond. And if I finish out my structure, I'll get 2 negative formal charges on the other oxygens. So that's a great Lewis structure for carbonate, but there was a moment there where I chose to put it on the right and I could have chosen the other 2 oxygens just as well. In other words, it was an equivalent choice. And when that happens, it's very important that I draw the resonance structures that would result if I just made that other choice. So for example, I'll have one with the double bond on the top, and I'll have one with the double bond on the left. So those are my 3 resonance structures for carbonate. And I want to point out that these are equivalent because when we ask you to draw Lewis structures, we will ask you to draw resonance if it's needed, and how you decide if it's needed is whether you have this sort of equivalent choice. We only want you to draw those equivalent resonance structures, usually, unless we're talking about something else, which I'll do an example of in a minute. So I want to talk about these 3 structures. It's important because we learned that a double bond would be shorter and stronger than a single bond. So is it the case that the molecule is just kind of switching back and forth all the time and the bond is just moving around from one place to another? That would be really difficult for the molecule to pull off because it would have to be shortening and lengthening bonds and the electrons would be moving. So all of that would be a lot. And in reality, each of these is just a model. All of them are not real. In reality, what we end up with is a sort of hybrid. So sometimes we'll draw a molecule with our single bonds, but then we'll draw dashed lines that sort of show there's some double bond character here in those oxygen-carbon bonds. And in reality, if we look at each one of these, if we take the average or the hybrid of the molecules that we drew, on the top, notice in the left one we've got a double bond here, we've got a single bond, we've got a single bond. So if I average those out, that's 4 bonds over 3 structures. So this is like a 4/3 bond. Or the bond order, we would say, would be 1 1/3. And that's true for all of the bonds. They are equivalent. What about the formal charges? Well, if I look at my oxygen on the top, in the right one, it's a negative. In the middle one, it's neutral. In the left one, it's a negative. So that's 2 negative charges across 3 structures. So it's going to have like a 2/3 negative charge. And that's true for all of the oxygens. They're all going to have that partial negative charge, a 2/3 charge, because it's going to be sort of the average or the hybrid of these equivalent resonance structures. So in reality, my molecule would be symmetrical. The bonds aren't quickly switching back and forth, but in reality, it's all spread out. This is a challenging concept to explain within Lewis structures because Lewis structures aren't the best way to model this. We're going to learn about some other models like molecular orbital theory and valence bond theory that are going to give us some more tools that we can use to model this that are going to start to make more sense. In the meantime, we draw these resonance structures because it's a relatively easy way to show the electron distribution within the molecule. Now, we can also use resonance to decide whether a structure is better or worse than another structure. Now, I want to show you an example where we're going to be deciding what the structure is. So we have a thiocyanate ion, and it has sulfur, it has carbon, and it has nitrogen in it, and it has a 1- charge. So it could be set up as NCS. It could be set up as CNS, or it could be set up as CSN. All 3 of those are valid ways that we could arrange those atoms, but in reality, probably only one of them is going to be likely. I'm going to draw these Lewis structures, I'm going to assign formal charges, and then I'm going to decide which one of them makes the most sense. So, I'll start with the one on the left. We have 6 electrons from sulfur, 4 electrons from carbon, 5 electrons from nitrogen, and 1 from that negative charge, which gives us 16 total electrons. I'm going to put in my single bond between each of those, that's 2 and 4, and then I'm going to fill in electrons 6, 8, 10, 12, 14, 16, that's all 16 electrons. My carbon doesn't have an octet yet, so I'm going to make a double bond from the sulfur to the carbon, and it still doesn't have an octet, so I'm going to do the same thing with the nitrogen. And when I'm done, I'm going to just assign some formal charges. So carbon came with 4, it has 4. Sulfur came with 6, it has 6. Those are both 0. Nitrogen came with 5, it has 6, so it gets our -1 charge. So that is our first structure that we drew. Now let's check out these other structures and see if they work better or worse. So again, I'm going to draw my single bonds, and then I'm going to fill in my electrons. That'll be 6, 8, 10, 12, 14, 16 electrons. My nitrogen doesn't have an octet, so I'm going to do the same procedure, erasing some of those electrons on the outer atoms and making double bonds to the central atom. And at this point, everybody has an octet. My formal charge on sulfur is 6. It came with 6, it has 6. Nitrogen came with 5 and it has 4, so that's going to be a +1 formal charge. Carbon came with 4 and it actually now has 6, so it's going to have a -2 formal charge. So overall, it's -1, which is what we're looking for, but we have a different situation with a formal charge there. Okay, last one, I'm going to do the same thing with my structure on the right, 2, 4, 6, 8, 10, 12, 14, 16, making my double bonds to the sulfur and calculating formal charge. Nitrogen should have 5 valence electrons, but it has 6, so it's a -1. Sulfur should have 6, but it has 4, so it's a +2. And carbon should have 4, but it's got 6, so it's a -2. All in all, we still have a -1 charge, but we have a lot more charge separation here, where we have formal charges on all 3 atoms. So if we're ranking these in order of which one's the best, my first one that I drew here is going to be number 1, because that one has the least total number of formal charges, and it only has formal charges on 1 atom within the molecule. I would put the middle one second because it has 2 different atoms that have formal charges, and it has that -2, and anytime you have a +2 or -2, that's definitely less likely. And I'd rank the last one the worst because that is charges on all of the atoms. If we look at our thiocyanate ion, we anticipate it's going to look like NCS, which is the one that we drew on the left. Another thing that we can notice about this is that in the center of the molecule is our carbon, which is the least electronegative of these atoms, and so that makes sense for it to be in the middle. Those less electronegative atoms tend to do more electron sharing and thus have more bonds and thus go in the middle of the molecule. Okay, so this is an example where if I asked you to draw the resonance structure of SCN and you weren't totally sure how to set it up, you could try these different ways of setting it up, and then you can choose the best one using your knowledge of formal charge, trying to minimize that formal charge because that's going to make the most stable molecule. That is our brief summary of resonance. I hope it's helpful, and I hope you have a great day.